Good morning, students. Today we are going for another topic, that is the applications of Gauss law. We left one topic, that is electric field due to infinite line of charge. Electric field due to infinite line of charge. Okay, this is the last application of Gauss law. Already we know that what is Gauss law. The total normal electric flux enclosed in a surface, closed surface, is 1 by epsilon naught times the total charge enclosed within the surface. Okay, so by using that Gauss law, we will find the electric field due to infinite line of charge. Nothing but what? Here we will take one line. Okay, in that line we place some charges. Okay, continuously we distribute a charge on a particular line. Okay, on a particular line we keep charges. Okay, the total charge here we are taking is what? Q. We are distributing the total charge Q on a particular infinite line. Okay, now due to this line of charge, okay, this is the line, we keep some charges on this line. Due to this, what happens? Around this charge, around this linear charge, we have an electric field. Around this charge, we have an electric field. On the particular infinite line, we continuously place the charges. Okay, due to this group of charges, due to this linear charge distribution, around this linear charge distribution, what we have? We have an electric field. Already we know the charge around the whatever the space around the charge is nothing but what? Electric field. Now we are going to find that electric field intensity due to this linear charge distribution. For that purpose, we took an infinite line. On that we distributed a positive charge Q. Okay, due to this charge, okay, we are going to find an electric field at a point P outside the line of charge. Okay, so this is the line of charge distribution. Okay, at point P, which is at a distance R. Okay, from the line of charge, at point P we are going to find what? Electric field intensity by using Gauss law. Okay, for that purpose, whatever the line of charge, okay, here at a distance R, okay, we are considering one point P. At that point P we are going to find electric field. For that purpose, we construct a cylindrical Gaussian surface. Whatever the dotted lines in the diagram represents what? A cylindrical Gaussian surface. Already a cylinder will be like this. Okay, cylindrical Gaussian surface. Gaussian surface already you know. Gaussian surface is nothing but what? It is an assumed surface. Actually, it does not present. Okay, we are assuming that for proving or for obtaining electric field intensity. So we are considering that Gaussian surface here. This is the cylinder. Now at point P we are going to find electric field. For that, so to find the electric field, we know that according to Gauss law, we have to find the first of all electric flux. Electric flux is equal to 1 by epsilon times the total charge. Okay, so to find the electric flux, now we construct a Gaussian surface which is a cylinder. Okay, through this cylinder, the flux is passing. Now we have to find the flux passing through the cylinder. Now that flux should be equal to 1 by epsilon times the total charge. Here, okay, now for that. To find the electric field at point P, now we constructed a Gaussian surface, cylinder surface. Okay, here. Now this at point P, we are considering a small element ds, whose normal is outward, and the electric field direction. See, the electric field direction will be always normal to the linear charge distribution. The electric field will be in this direction. Okay, not in this direction or in this direction or downward direction. The charge is here. The electric field will be outward to the positive charge. Okay, so whatever the charge we place, the electric field direction will be upward. So the electric field in this direction and the ds bar direction, both are in the same direction. Now flux passes through this small element. Here, see, already we know that we have to find the flux passing through the entire cylinder. Okay, here the cylinder will have curved surface area and two circular ends. If we consider this is a cylinder, okay, it has a curved surface area and two circular ends. Now the flux passing through the entire cylinder is nothing but what? Flux passing through the curved surface area and flux passing through the circular ends. That is the total flux. Okay. Now to find the flux passing through the curved surface, we took one small element on the curved surface. ds normal is outward and electric field is also in the same direction. Now the flux passing through this small element will be d phi is equal to E dot ds according to the definition of flux. Okay, it is the product of dot product of electric field intensity and the area, small area ds. Okay, so E dot ds is equal to how much? E ds cos theta. Where here theta is how much? 0. Cos 0 is 1. So which is E ds. Okay. Now flux passing through the entire curved surface is how much? That is phi. Here, if you observe, here we also have circular ends. Here through the circular ends, the whatever the flux is 0, because here whatever the circular end, if we take a small element ds on the circular end, its normal will be like this and electric field direction will be like this. The angle between these two is 90 degrees, cos 90 is almost 0. So the flux passing through the circular ends, both ends, left and right end will be 0. Whatever the flux passing through the curved surface area will be present, it is not equal to 0, will be present. That will be equal to phi is equal to, now we got d phi, the small element. Okay, flux is how much? D phi e, which is E ds cos 0, that is E ds. Now integrating this small element, okay, adding all the small elements to get entire curved surface area, whatever the flux passing through the entire curved surface area. So phi is equal to integration of E dot ds, integration E ds cos 0 nothing but 1. So integration E ds. Here the electric field throughout the cylinder will be same, uniform. So that is constant. So electric field is taken outside, integration of ds. Okay. Now integration of ds, the entire surface. It will use the entire surface, entire curved surface. What is the area of the curved surface of cylinder? 2 pi rl. Already in the previous class, we discussed the electric field due to uniform charge cylinder, where we discussed that the area of the curved surface area of the cylinder is 2 pi rl, where r is the distance of the whatever the radius of the cylinder and l is the length of the cylinder. Now the whatever the curved surface area is given by 2 pi rl. So now the entire flux passing through the curved surface area is how much? E into 2 pi r. Okay, this is the flux. Now according to Gauss law, this flux should be equal to how much? 1 by epsilon naught times the charge. Okay, 1 by epsilon times the charge. Now E into 2 pi r is equal to 1 by epsilon times the charge. But we know that here whatever the charge is linear charge distribution. On the line we are distributed the entire charge. Okay, now already in the previous class we discussed that linear density lambda. Linear density lambda is nothing but what? Charge per unit length, Q by L. Q by L. So Q is equal to, from this Q is equal to lambda into L. Now in place of Q, we are going to substitute lambda L and send this 2 pi r right side. 2 pi r epsilon naught. Okay, L will get cancelled. Hence, what will remain? Lambda by 2 pi epsilon naught r. So now electric field intensity due to infinite line of charge is how much? Lambda by 2 pi epsilon naught r. Okay, this is what the electric field intensity. Okay, this is the last application from. Okay, these are now the entire applications of Gauss law will be completed. Okay, in the next classes we will see the new unit. Okay, see. So this is what electric field due to infinite line of charge. Now, by observing this class, okay, by listening this class, just write down the notes. Okay, prepare your own notes by watching this video. Okay, thank you. Okay, we will meet in the next class.